Hello everybody, let's welcome our last speakers for today, Hee-Jin and Chang-Yeon.
Right.
And they talk about HackDMI or HDMI, and the stage is yours.
Yes. Hello, I'm Hee-Jin Jung, and thank you for coming here. And the topic I will talk about today is HackDMI. The table of contents is as follows. First, I'd like to give you a quick introduction to me, my team, and today's topic, HDMI. I will explain what HDMI is and why we choose it. After that, I'm going to talk about the previous research and DDC, CEC, and AIC protocols that we regard as attack vectors. Finally, I'd like to introduce you to each protocol fuzzer that we've made and tell you about the results. First of all, my name is Hee-Jin Jung, and I am a Vulnerability Assessment Track Mentee of VUB, which is the next generation security reader training program in Korea. And I major in software at Sungsil University.
And my name is Chang-Yeon Moon. I'm also VUB mentee in South Korea. Just student, yeah. And it's our first time to speak at a conference, so we are really nervous now, but we will do our best. Actually, I'm here as her helper and photographer, so please only focus on her. Thank you.
We are both the member of the team Shingi Hajin, and we worked on the topic of vulnerability assessment for HDMI-based embedded device at VUB. Our team is made up of 2 mentors, 1 PA, and 5 mentees. And what is HDMI? HDMI is provided for transmitting digital television audio-visual signals from DVD players, set-top box, and other audio-visual source to television sets, projectors, and other video displays. HDMI can carry high-quality multi-channel audio data and can carry all standard and high-definition consumer electronics video formats. Content protection technology is available, but what we are interested in this time is not content protection. We are interested in the various protocols that exist in HDMI that are likely to be attack vectors. Maybe even without this explanation, you may already use HDMI to connect your laptop to a TV or beam projectors. And also, I connected my laptop with HDMI today. What's interesting here is that HDMI not only delivers the audio-visual signals, but controls, status, and data information in both directions. Let's talk about this in more detail in the HDMI protocol section. Then why HDMI? The first reason we choose HDMI is that it has a high utilization rate. However, the weakness of the HDMI is that it requires a direct line connection, but considering the usage rate of AV devices, the impact of vulnerability is huge. The second reason is that it provides various functions as well as the video data transmission. As mentioned above, HDMI supports not only the TMDS protocol for video transmission, but also the various protocols such as CEC, TDC, AIC, and HEC, which provides various functions. Such diverse functionality were thought to make it convenient to use, but also created the probability of vulnerabilities. Finally, we wanted to do some research on attack vectors that are not well considered. Not many people have researched it, but we wanted to do it because we thought it is valuable enough. This is the previous talk about HDMI. Hacking display made interesting at Black Hat Europe, and what the HEC at FUFOCon, and high-def fuzzing at DEFCON. The one day of the HDMI was the vulnerabilities of the memory corruption type that occurred as CEC and DDC protocols. Now, let's talk about the HDMI protocols. We are going to talk about 3 protocols in order: DDC, CEC, and ARC. HDMI has the 4 separate channels. It is the TMDS, CEC, TDC, and HEAC. TMDS is used to carry audio and video data. The DDC channel is used by an HDMI source to determine the capabilities and characteristics of the sink by reading the E-EDID data structure. HDMI sources are expected to read the sink E-EDID and to deliver the audio and video formats that are supported by the sink. In addition, HDMI sinks are expected to detect info frames and to process the received audio and video data. The CEC channel is optionally used for higher level user functions such as automatic setup task or task typically associated with infrared remote control usage. And last one, HEAC is optionally used as a high-speed bidirectional data channel and stands for HDMI Ethernet and audio return channel. The 4 protocols mentioned above are mapped from the actual HDMI pins as follows. TMDS is from 1 to 12, which is marked yellow. And pin 13 is the CEC, and pin 14 is the utility line used by the HEAC. 15 and 16 are SCL, SDA, and 17, 18, and 19 are intern ground, VCC, and HPD. Here, we were interested in different functions such as carry controls, status, and data information, rather than video data transmission. In addition, the protocol supports both directions. So today we are going to talk about these protocols. First, DDC. DDC stands for Display Data Channel. DDC is used by the HDMI source to read the sink E-EDID to discover the sink configuration and capabilities. More easily illustrated, when you connect the TV and the laptop with the HDMI, the sink TV will send the E-EDID data to the source laptop. So what data does DDC send? It's called EDID. It's Extended Display Identification Data. The EDID is a metadata format for display devices to describe their capabilities to a video source such as graphics card or set-top box. This format is defined by a standard published by the VESA. However, EDID is for PC monitors, and E-EDID is an extension of the EDID used traditionally to illustrate more advanced features. Then why do we need E-EDID? For example, PC monitors generally do not support audio, so a traditional E-EDID structure would not account for this, whereas an E-EDID would. So it sends the E-EDID data. The E-EDID data consists of EDID 1.3 and the CA extension. EDID 1.3 and CA A61D have the following structures. Because the data sent by the FUZZER is also this E-EDID data, so we need to know a little bit about the data structure. EDID 1.3 includes the information such as horizontal size, vertical size, and color characteristics. There is also an extension flag, which means that the extension data follows the EDID data. If you are not sure what the EDID is yet, turn on your laptop. If your laptop is now connected to the TV or monitor with the HDMI, you can probably find the E-EDID in your laptop. I checked in Windows, Ubuntu, and macOS. On Windows, it is stored in the registry. And on Ubuntu, it can be found in the path sys class DRM. And on macOS, you can check it through the I/O registry. Then, how do we send this E-EDID data? The HDMI transmits E-EDID data over the I2C bus. As you know, I2C is the serial computer bus invented in 1982 by Philips Semiconductor. It is widely used for attaching lower-speed peripheral ICs to processors and microcontrollers in short-distance intra-board communication. I2C uses only two bidirectional open collector lines, SDA and SCL, pulled up with resistors. Typical voltages are 5 and 3.3, although systems with other voltages are permitted. We used Arduino to transmit E-EDID data directly. You can use other things, but you can easily use I2C slave mode with Arduino compared to Raspberry Pi. You can connect the resistor and the wire to the each pin as shown in the picture. The wires connected to the breadboard in turn are SCL, SDA, ground, VCC, HPD, and each line is connected to the pin that is mapped in HDMI. With this connection, the hardware preparation is finished. Now, we can transfer the actual data through the wire libraries supported by Arduino for communication with I2C devices. Note that it uses a 32-byte buffer, therefore any communication should be within this limit. Exceeding bytes will just be dropped. The main functions for data transfer are begin, onRequest, onReceive, read, and write. As mentioned above, since the buffer length is 32, if we send the E-EDID value of 128 bytes, the data we sent is dropped. Therefore, I modified the buffer length in the header file to 128 as follows. As a result, E-EDID data can be transmitted as shown in the picture. On the left is a code written using the Arduino IDE, And on the right is the result of sending E-EDID data to the laptop with Arduino. The second protocol is CC. Now, your laptop and smartphones are connected to your TV without any problems. Of course, it's possible to connect multiple devices, as shown if you have multiple HDMI cables. By the way, how many remote controls do you need to control each of these devices? Yes, the answer is in the CEC protocol. CEC stands for Consumer Electronics Control. CEC is a protocol that provides high-level control functions between all of the various audiovisual products in a user's environment. CEC provides a number of features designed to enhance the functionality of devices within an HDMI system. AnyNet Plus, EasyLink, EasySync, rather than CEC, can be more familiar. It's the trade name for CEC. CEC is protocol based on the bus system and therefore cannot alone ascertain the physical connectivity of the network. So, it uses the DDC protocol to allocate the physical address to the devices in the network. All CEC devices therefore have both a physical and logical address, whereas non-CEC devices only have the physical address. The physical address is 4-digit long, and therefore it has a 5-device deep hierarchy. When a physical address is allocated, then allocates the logical address. The root device TV has the 0000, and the devices connected to the TV have 1000 and 2000. In addition, the DVD and STB connected to the amplifier become 2.1 and 2.2. Logical address defines a device type. For example, TV is 0 and a recording device is 1 or 2 or 9, depending on the device type. Logical address is allocated through polling message. If it is a recording device, it sends a polling message to the first of 1, 2, and 9. If polling is acknowledged, it takes the next address. If not, it stops the procedure and retains that address. The CEC message frame has this structure. The first is the start bit, followed by the header block and data blocks. The start bit is a special bit indicating the start, and the header block and data block are each composed of 10 bits, which consists of 8 bits of information bits and 2 bits of control bits. The data block is optional. Information bits and control bits are described in detail in the next slide. First is the header block. The information bit in the header block contain the logical address. The addresses of the initiator and the destination are each composed 4 bits. The control bits has the same format for both the header block and the data block. The control bits include the EOM bit and the ECK bit. the EOM bit stands for end of message. So if the current block is followed by one or more blocks, it becomes 0. And if the current block is the last one, it becomes 1. The ACK bit stands for acknowledge, which contains the value of acknowledge of the data over header block. The data block also consists of information bits and control bits. The header block is essential, but the data block is an optional block. The data block has the data block 1 and data block 2. Data block 1 contains the OP code in the information bit, and data block 2 contains the operand. The operand has a dependency on the OP code. If the OP code is 32, which corresponds to the set menu language, the operand will contain the language you want to set. Data block 1 is one block, and data block 2 can be multiple blocks, depending on the OP code value. However, the maximum message size is 16 blocks. That is, the message with the maximum length is 1 block of the header block and 1 block of the data block 1 and 14 blocks of the data block 2. So how do you send this CEC message? While you may have been frightened by the transfer E-EDID data at DDC part, CEC messages can be sent easily. There is a USB CEC adapter communication library called libcec. It can be found in the GitHub. If you have a USB CEC adapter created by Pulse8, you can send a message. Of course, other adapters are also supported, and if you are having trouble to buying a new adapter, you can use Raspberry Pi. With libcec, you can send the CEC message as above. But this library is so well made that it can drop our fuzzing data as well. So we will not use this library when fuzzing. Since the adapter shown above is a USB CEC adapter, that the data can be transferred via the serial communication. Of course, you can use Pi serial. You can send messages with just 3 lines of code as above. Now, you can control the devices connected by HDMI with a single remote control. However, if you need an audio cable or several HDMI to use home theater, another inconvenience arises. So the AIC protocol solves this inconvenience. If you have seen the word AIC on the back of your TV, you may already be benefiting from this protocol. AIC stands for Audio Return Channel. AIC function allows delivery of an audio signal from an HDMI sink to an HDMI source in the reverse direction to the TMDS signal. The figure shows that the TMDS signal, which is audio or video data, is transmitted from the source device to the sink device. And the AIC protocol goes from the sink to the source in the reverse direction. Then how to use AIC? In order to use AIC feature, it is necessary to discover and control the capabilities of the devices in the respective paths using CEC. There are two types of AIC initiation and termination, from AIC RX device and from AIC TX device. First, let's look at the from RX device. In the case of initiation, an AIC RX device activates AIC RX functionality and send the directory addressed initiate AIC message. If follower sends a feature abort message, the AIC RX device assumes that the follower do not support AIC feature. If the follower sends a report AIC initiating message, this means three things. 1. The follower is an AIC TX device. 2. Its AIC TX functionality has been activated. 3. It transmits audio stream via the audio return channel. In the case of termination, the RX device shall send a directly addressed terminate AIC message to TX device. After that, the TX device shall stop transmitting its audio stream. Then deactivate the AIC TX functionality and respond with the directly addressed report AIC terminating message. And the RX device may deactivate the AIC RX functionality. In the case of where an AIC TX device wants to initiate an audio return channel, then the AIC TX device may request to initiate the audio return channel by sending a directly addressed request AIC initiation message. Terminate also sends a request AIC termination message instead of terminate AIC. When using the audio return channel, the TV wants to find which audio formats are supported by an amplifier. It is also through the CEC by sending a request short audio descriptor message. The process of obtaining the audio format is shown below. So far, we have looked at a brief description of the DDC, CEC, and AIC of the HDMI protocols and how to transmit its messages. Now, I will use them to create a fuzzer. The order is the same for DDC, CEC, and AIC protocols. First, DDC. The target device is an HDMI source device. You can probably guess the reason. The DDC protocol allows the sync device to send the E-EDID data to the source device. Therefore, the source device, which is the device that received the data, was targeted. Source device includes desktops, laptops, and smartphones. We used the Arduino Mega 2560 and transmitted the data via the Arduino's wire library. Also, we cut and soldered the HDMI cables for more reliable data transmission. If you cut the HDMI cable, you can get 19 pins and a wire connected to each pin. We connected the appropriate registers and wires to the required SCL, SDA, ground, VCC, and HPD locations and solder them to make the same cable as the last picture. Then connect each of the 5 jumper wires to the Arduino. It will now send the E-EDID data. It consists of E-EDID 1.3 and CA861D. At this time, if the value of the fields such as header, padding, and checksum, which are marked in red, are set where the fuzzing effect can be enhanced. We created the data in the above 3 ways when mutating. First, each structure of EDID, and second, random among structures that are likely to cause vulnerabilities, and finally, a random value for all data. We used bit flip, swap, and shift as mutation method. One more thing to note here. To fuzz through the HDMI cable, the process of connecting and disconnecting the HDMI should be repeated. However, if you have to plug in and out every time you send data, it's very inefficient and it will not be called a fuzzer. This is confirmed by the HPD signal. So we repeatedly send low and high to HPD pin, giving the same effect as connecting and disconnecting HDMI. Now, CEC protocols. Any devices that support CEC can be the target device. For example, smart TV, beam projector, set-top box, smartphone, game controller, and so on. In the case of a smartphone, it is highly likely to purchase a new adapter. Make sure that the adapter also supports the CEC protocols. For CEC protocol, whether to support CEC rather than the type of device is a more important factor in determining the target. For the CEC fuzzer, all you need is a USB CEC adapter and the HDMI cable. Let's first look at the code that sends messages to the CEC adapter without using libCEC library. Before that, you've probably seen this picture. When data is transferred using the adapter, one block is represented by 4 bytes. More precisely, the information bits in a block. This works for both the header block and data blocks. The 4 bytes consist of message start, message code, message value, and message end. The actual data value contained in the information bits are stored in message value. Message start and message end are the bytes representing the beginning and end of block, respectively FF and FE. Message code can be thought of as control bits. We created fuzzer for the 3 parts of the CEC message frame. First, it is an OP code. 3.6 was excluded because it is OP code to power off the device. And here, the message to be transmitted has a structure of message start, message code, and message value, message end. At this point, you can see that message code is different, which can be found in the libcc code in CEC adapter message code. For basic message transmission, you need to know about 4 message codes in your code. In particular, OB and OC are message codes related to message transmit. I said that the message code is similar to the control bit. For the EOM bit of the control bit, that is represented by OB and OC. The ACK bit is also similar. The second is the operand. We randomly selected the value from 0 to FF to transmit the operand of 14 blocks. The header block is fixed to the logical address of the target device. In the case of an OP code, to increase the probability of a crash, we use the list of OP codes that are likely to cause vulnerabilities. Finally, the message length. In the case of the CEC protocol, the maximum message size is fixed to 16 blocks. That is 160 bits. In addition, each block is recognized as a header block on OP code and operands in order. Therefore, data of various message sizes were transmitted, including messages that exceeded the maximum size. The next protocol is ARC. In the case of ARC protocol, similarly to CEC, devices supporting ARC are targeted. For example, there are home theater and soundbar. What is interesting about ARC? We thought vulnerability may exist in the area where the audio signal is returned via ARC. Since devices that support ARC use lower versions of codecs, the audio codec one-day vulnerability is also likely to work. Now, let me tell you about the results we have obtained through our FUZZER. This is the result of FUZZER shown above into the setup box. And unfortunately, we haven't found an exploitable vulnerability, but we think it makes sense in terms of showing that it is possible to attack via HDMI. Also, the last one was ignored because it has already physically contact. I think this means that there are those who are interested in attacks via HDMI as well. First, if you look at the DDC, you can see that the kernel panics and fails to reboot when you send the EDID data. Also, we can see that the value is modified to 6.1 that we sent. The following is the CEC. In the memcopy function, you can see a 1-byte stack overflow resulting in a memory leak. In closer look, the top part of the right function is the CEC message value we sent, and we can see that the onTransact function in libHDMI CEC contains the header block and data blocks we sent. The readInt32 and readCstring functions are just that part. And if you look at the onEventUpdate function in libHDMI CEC JNI, copy it to V8 using the values received above. At this time, a 1 byte overflow occurs. In fact, we want more influential results and have done more work than what we wrote. Fuzzing with a real HDMI cable creates a problem of speed and stability. At the time, we thought that the graphics driver vulnerability is highly influential. So we made a graphics driver fuzzer of HDMI on Ubuntu. So I'd like to briefly introduce the Ubuntu DDC fuzzer that we made. Actually, there were a lot of difficulty in making this. The process of creating this fuzzer can be summarized in 4 main steps. First, with source code auditing, I found the HDMI E-EDID getting part in the graphics driver and the IOCTL code. After that, I checked the code stack with ftrace. The third, hooked and mutated with kprogs. Finally, we completed the program by calling IOCTL with libdrm. The presentation so far can be summarized in these 3 pictures: the DDC, CEC, and AIC protocols. And it is our future work. First, vulnerability assessment with E-AIC protocol added in HDMI 2.1, and we refine the vulnerabilities of HDMI on graphics driver to save the world. And also, we want to study more about attack vectors that are not considered well. Source and images are as follows. Thank you for listening so far. And I do not speak English very well, so if you have any question, I will stay in Germany until Friday. So come with me and talk together after this session. And of course, you can also ask questions at this email address. Thank you so much.